My goal for this talk would be to give you an understanding what it is, because all of the talks like, yeah, this is easy, let's spend 30 minutes talking about this, and at the end every speaker says, yeah, it needs to click, then you will understand it and use it. So I would try to explain you what it is in a very simple way. And for this, before talking about how I used it for the customer project, I would start by talking about recursion in general. You probably cannot see it yet. I will make it a little bit bigger. This should be okay, right? Okay, so recursion, the most common example of recursion is taking a factorial, like multiplying n by factorial of n minus 1 down to 0, and factorial of 0 is 1. So let me just represent it like this. This is a recursive definition of factorial. This goes exactly like I said. If n less than I, so we need to optimize, right? So we have an opportunity to make this talk useful. So we optimize the definition of factorial right now at the beginning. So another definition would be like this. So we take all of the numbers from 2 to 10 and then reduce the list by multiplying them all together. The results should be the same because we're basically doing the same thing. So let's just output factorial R and factorial M. Yeah, 120 in both cases. So I would argue, I've been thinking about asking you this question, but yeah, this is kind of very vague definition. So I would argue that the second definition is better if you look at it from the design perspective. And the reason for that is that you define what to do, but you don't define how to do it. So you say, okay, just multiply all of the numbers from 2 to n, and how to do this is encoded in the implementation of the reduce method. Whether we in factorial R implementation, we stating explicitly that the factorial R calls itself until it's time to return n. Does it make sense for you? Can you follow, right? Good. That's already very good. So how is it possible that we abstract the definition of how in the second case? Because reduce uses an functor. Does it scare you? Do you know what functor is? Not all of you. Okay, the functor is an abstraction which takes some kind of container, and then it knows how to apply function to the internals of this container and return back the container with changed internals. So basically, the functor abstracts how do you go inside and how do you return the stuff back. The container can be anything. So the factor for the list knows how to go over each element. The factor for option knows how to deal with empty option or with full option. The factor for either would know how to deal with right and left side. Or if it's Scala to 13, then it knows how to deal with right side by default. So we would like, for our recursive implementation, we would like to specify this kind of abstraction so that we don't define explicitly that the factorial R calls itself. Instead, we want to say it calls something which is an abstraction of recursion. In functional programming, we know how to do this. We just introduce a function parameter, which we later can call. Something in that form. So if we are operating with ints, then we take a function from int to int, and then we can call this function as an abstraction of a recursion later. So basically, it's very same implementation like here. We just pulled out the notion of recursion, of calling itself, and replaced it with this function f. Does it still make sense? Okay. We're almost done. Now there is a question, okay, but somehow we need to get this function f, we need to pull it out from somewhere. So what do we do? How do we implement this function f? This line rec represents another approach to the same problem. Like we can think about this function f not in terms like where we can get this function to feed it into our implementation. Instead, much better would be if we could define a function rec which would take any simple function f and make a recursive function out of it. So for example, we would say, okay, this is a one-step definition for factorial calculation. Then we feed it into the rec, and we get this implementation of a recursive function automatically. So basically, the rec is an abstraction, still an abstraction of recursion, which transforms a function, a simple function, into a recursive function. Okay? So I will show you in a moment how to implement this function. The problem with Scala at this moment, if we start to implement the rec, it's kind of, by definition, it's a recursion. So we need to provide types everywhere, and it will just slow us down. So I will instead show you quickly how this can be done in JavaScript. Everybody knows JavaScript syntax? Yes? No? Okay. It's not very different from the Scala. This is a definition of factorial in JavaScript. The same stuff. If n less than dry, we return n. Otherwise, we multiply n by factorial of n minus 1. The same as we had in Scala. We have console log instead of print. Let's execute it. Recursion JS 120. So everything works. So let's go the same steps and think this is the definition of function, which is taking function f as an abstraction of recursion, and it produces the same result as before. This is the same definition as we had in Scala, just with a little bit different syntax. So what do we do now? So now we need to define a recursion function which takes f and returns f applied recursively, right? F applied recursively means we kind of apply f to f to f to f to f, and we do this infinitely. We applying f. This is the definition of recursion. So basically, we kind of done. Thank you for your attention. Now. I will not type in this stuff infinitely because we have only 45 minutes. But I would say that if we have those things infinitely, then it doesn't make difference if I put one more f here, right? So you wouldn't notice because here in ellipsis, many of them. So I could say same way the rec f. I would say basically I could take one f out of here and put it on another side. That mathematically it won't change anything, but it's still our definition of rec. So that's how we define a recursion. This is the pure definition of abstraction called recursion. If we now apply this function rec to the factorial, then we will get the definition of factorial as before, and we can actually remove this guy and print the result. So, you still with me? You still following? I mean, that's very simple things we're doing here. It probably just like strange because how come we apply an rec to the simple function and getting the recursion function? But the wonder is like this definition. The programming language figures out how this implementation of rec should look like so that this equation holds. And that's what allows us to define the factorial in a way we did. So I will just demonstrate it to you. Yeah. Rec. Unfortunately, I cannot really demonstrate it here because JavaScript tries to evaluate rec of f here before applying f. So it goes down in this recursion tree infinitely. Actually, it's what we wanted. But we have no possibility to execute this branch here because first the rec gets evaluated. So we would like to first execute the f, and only if f is not exiting and calling the f here, then we would like to evaluate this those contents, right? It's easy to do. I will show you yet another language, Haskell, and the reason why it's because it's lazy, so it won't have the same problem of going down the tree if it's not needed. So this is the definition of our function. It takes a function f and an n, and it has the same definition as before, as in JavaScript, as in Scala. Right? So now we can define an rec function, and it's really beautiful in Haskell. It's the same definition, just very clean. The factorial of n then defined exactly as before, as applying the rec function constructor to the function we have. Oh, sorry, there's a typo. And providing an n. Actually, we even don't need this n. We can make it a partially applied function if you like to. And then we can print out what it is. What the value of the factorial of 5 is. Don't pay attention to this print line show and main is kind of Haskell stuff. What do we have here? So the Haskell implementation is lazy, so it evaluates our result correctly. We can do the same in recursion for JavaScript implementation. We just the trick is to prevent it from evaluating, and we can do this by converting it into the lambda function. So we say, okay, before evaluating this, you need to get a something a, some parameter a, which you then can apply. That's a very kind of easy trick. So instead of something which is a value, basically, we make it a function. But the function giving some argument a will produce the same value as it would without having this argument at all. So it's basically just a trick to tell the compiler, please do not evaluate it before we tell you. And now we have the same result as before. So this factorial definition now works with this definition of rec. What we achieved for now, we have a function rec, which is concentrated pure abstraction of recursion. We can have it implemented in lazy language like Haskell. We can have it implemented in ergar language like JavaScript or Java or Scala, sorry. And having this abstraction, we can convert any function which is not recursive into something which is recursive. any function. We need to do this at some point. So let's specify how it will look like in Scala. So for simplify the task, I will just take the definition we had here. So this is the definition of our rec function, and it. Oh, sorry, not from Haskell. The Scala is not lazy. So, so this is a definition of our rec function, and it takes an f and an a, and it produces basically an f of rec of f of a. The definition is the same as here. I just changed the const to def to make the compiler happy. Of course, it will not work because we have a recursive definition, so we need to provide a type here and the types for f and a. I will make it polymorphic from the beginning because it's not only applicable to functions working on ints or longs or something useful for factorial. It's basically useful for any function which could be made, which at some point we might want to make recursive. So I will define this scope class, which only has a purpose that we don't need to care around the type parameter of our function. So I could have specified this a somewhere here. It would work, but I need to repeat it again and again, so I don't want to do this, so I pushed it up. So the a will be of type a. Then the result of this execution should be a function which takes an a and returns an a. I'm just following the types. Type f of a would be something which takes an a and returns an a. This guy. We said that rec itself, it takes f, which is of type f of a, and returns something of the same time. It just makes it recursive, but the type stays the same, right? So I will call it ft, f transformer, and it takes an f of a and returns an f of a. So this is the guy here. And then we can say, okay, the rec is f transformer, which is taking f of a, and f is an f of a, and a is of type a. So it should compile. Let me check. It compiles. Let me remove those prints. So now we basically have this abstraction of recursion in Scala, which we can define for any type A. To demonstrate it, I will define the factorial function. So what I am doing, I'm creating the scope of type int, and I'm using the rec function to convert our fec function here into the recursive definition. Right? Let's see what it will produce. The same result as before. So basically it works. Does it still make sense?
Well, I see the function. Can you scroll up? No, the code.
So the fact function, again, it has this abstraction of recursion here. It's coming from the outside. And it's used inside exactly like you would use an abstraction of functor in your code which maps over a list. You don't have this definition hard-coded. It's a parameter. And in order to make this definition, getting this definition easy, we're defining a function which is able to produce those functions, by converting a normal function into a recursive function. Okay, this definition of rec as we had in Haskell. Just a little bit of terminology because I cannot leave it on this in this state without saying this. If I replace rec f with an x, I will get a mathematical equation x is equals f of x. This is called fixed point in mathematics because it means there is a parameter x for which the function f will produce the same result. For example, if we take something like a cosine function, and calculate it repeatedly, and this kind of we're just assigning the result of the calculation. I am basically replacing an f here with the cosine function, just to give you an example of a fixed point. Okay? So if we now output the value of x, it will be of this form. The interesting point is like if I apply cosine one more time, then the value will not change. So basically it's stable point of this function or fixed point of this function. And this is why this approach to recursion called fixed point. That's where it comes from. Basically, if you look one more time at this definition of rec, it's very close to the mathematical definition of fixed point function, and this produces the recursive functions. If it doesn't make sense now, I hope it will make sense if we make it a little bit more complex. Yeah? This is the factorial function.
What makes it fixed point?
The fixed point of function is the result of the application of rec of f fag, and it's something we cannot tell what it is. This is something which runtime gives us. So basically, instead of this x we had, which is a double or float point, we have a function. So that the runtime iterates over this function until it has some representation which is a fixed point for the function we gave. So, okay, making it a little bit more complex, I'm familiar with the concept of reified types, like reified representations. It's simple. The names are very intimidating, but the concept itself is very simple. Let's say I have something like 5 times 6 in the code. I can represent it as that data structure by saying, okay, I have something like class multiplication 5 and 6. And it has an apply method which produces 5 times 6. So of course I can replace those with x and y of some type, and then so what I did, I took something like which is represented as logic in the code, like idea represented in the code, and represented as a data structure. Why would I need to do this? Sometimes I just need to pass logic around. Not always it's representable as a function, and I can represent it as a data structure so that I can store it, I can move it around between computers and so on. So if we now think about, okay, we have this rec function which generates recursive representations. What can I do with that? Actually, I would say I can represent it as a reified in a reified form. So I'm taking the Haskell definition now, and I'm saying this is a case class. Rec, we just set it as fixed point, so let me call it a fix. Okay, it will stay rec for now. Rec and f is an argument of this function rec, but now we represent it as a data. So we have this f defined as a type parameter. You just lift we just lifting the implementation itself to the data type, and parameters it takes automatically become type parameters. So like from function to type, from function parameter to type parameter. Okay, and we need to name it somehow. Let's call it A, and it's of type f of rec of f. Okay, not quite. The f here takes a rec as a parameter, so we need to say it to the compiler. Okay. Just changing the representation from the from logic into the data. It's literally changing it bit by bit. I'm not doing anything fancy here. So we can try to compile it. Thank you. Now we doing advanced type manipulation. So congratulations. Oh, please. Okay, it compiles. So we now have this definition of rec. Let's call it fix, as I said, just so that we stay in the naming convention space. And by convention, this parameter called unfix. It's kind of fix of unfix of fix of unfix, and so on. Yeah, that's it. So that's the fix point type, and it's useful to represent recursion on the type level in your code. For example, I will now just build a list for you. Not quite a list we have in Scala, but very similar. So the list is built using head and tail, like the first element and the rest of them, and the last element is usually followed by nothing, like an empty list called nil. So this is a definition of our f-list abstraction, and it has two members in its data type, like f-cons for fixed point type cons. It has a head and a tail, and nil, which is only one. And then we can define the constructors for nil, which is a fix of f-list. We're just applying our recursive type we just created sorry, to the f-list we are building. And you probably can guess that the next one will be called cons. And it combines, of course, the head and the tail as fcons. And that's pretty much it. What would happen if we would not use the fix here? We would have a type which is recursive. For example, if we build our list like that, without fix, it would be nested f list for this one. Nested for this one, nested into the f list, into the f list, into the f list. So we would have 4 levels of recursion on the type level if we wouldn't use this fix. But fix allows us to define it like a single type without nesting, because fix incorporates this notion of recursion in it. Let's see what it outputs. So in reality, it's the type of fix of fcons, fix of fconf, and so on. So literally, if we would not use fix here, this would be fcons of fcons of fcons and of fnil. It is possible to represent the tree the same way. So we just have the leaves and nodes, and the approach is the same. That's like the leaf is a value of the leaf, and the node has 2 branches. It's the same approach, so that we can have a nice representation with a single type parameter. Don't focus on that. 2 constructors for leaves and for nodes. And we can build a tree. And output it. Oops. Oh. This is the tree. The type would be quite complex, but in reality, it's just a fix of 3f. Okay. So we done with all of those fixed point types and so on. This is not going further than that, really. You now know it all about them. The fixed point types is like something special, and of course there are ways to manipulate them, patterns to manipulate them. The same way we have object-oriented patterns for object-oriented programming, like the Gang of 4 book. Who's familiar with this object-oriented patterns? Yeah, you have, for example, then flyway pattern or observer pattern or some other patterns, and each of them describes how you can combine objects in order to achieve some desirable functionality. For example, if you need to represent one object as an instance of another object, you would apply a decorator pattern and so on. So basically, it's a recipe how to behave, how the developer should behave, what the developer should do in the case if some functionality needs to be implemented. The same way it's here. The patterns to manipulate those recursion fixed point types called recursion schemes. They have usually Greek names, and it's kind of what scares away many people, but this is nothing different from object-oriented patterns or from functional programming patterns like functor, monad, and so on. Just names are scary. And I believe the reason is like the object-oriented patterns, they all have very nice names because the Gang of 4, they wanted to publish a book and to sell it, and that people use their patterns, so they gave easy, meaningful names, and the recursion schemas, they described in scientific papers. I don't know what the goal of scientific papers, but the names are kind of, don't really follow this schema. Okay, how this approach can be used, and I will hopefully Yeah, probably not. I will hopefully will be able to show you at least one schema, recursion schema. So the project I did was for this customer. They building factory lines for cardboards. So this the line itself looks like that, nothing very fancy. On the inside, quite the opposite. So there are lots of components which work together to produce the cardboard from just normal paper. And of course, we now have Industry 4.0, so they want to measure everything on the mechanical level, on the electronical level, and of course derive numbers for the business. So this is what I did for them. You probably cannot see this clearly. Those are different charts we have here. For example, at the top, this is just a business view. At the top, we have 5 tabs. Each tab has a number of charts. The data itself is like on the bottom level, looks like that. You have some metric and number for that, and the time. In this example, the time is like in the metric is calculated monthly. If there are multiple metrics, then you have multiple names. That's it. Here I tried to make a screenshot with different possibilities to select what should be measurement in relation to what. So basically, at the top we have a time, and then you have the possibility to group this according to different time intervals and apply different filters. And here you can select different possibilities to combine the data. The interesting part is like the majority of the time spent for producing those charts is spent on the database level. So the calculation itself is very quick in relation to that, which gave us an idea to do the following. The client gets by default the definition or the data for the full combination of those things. So if you count, then you will see this guy is a time interval, and then 4 different toggles or selects, and the same is here. So this is a time interval and 5 levels of nesting for each of the inputs. And then if the value of the input changes, then it will be the another name. So it's a nested structure, and the client implementation can just go down this tree and select the data set suitable for the current user's inputs. Okay. So we represent everything as an entity which has a time and an ID, and each entity they combine like they have many different specific to each entity settings, parameters, properties. So they combined like this is an area which is a machine, then people who work on them, then people produce the material of different quality. This material will be sold to different customers, and during this production you can have incidents. So basically this is a 5-level structure which is represented like this. An area has shifts, and shifts has grades, and grade has orders, and orders has stops, and stops don't have anything, which is kind of very hard-coded. So we can start with replacing the children type as a type parameter. It's the same, just instead of telling exactly what the child type is, we say, okay, it's of some polymorphic type. Then we need to deal with this guy because it's different from others. We will say, okay, it will have children. We just never assign anything to this field. Okay, and this allows us to represent the whole data structure as one case class, which has an entity and the children of which is a sequence of some type A. And for example, we can represent with this structure a case where for the some calculation, we don't need information about the quality and the NORA. We just need shifts and stops. We can encode this like this. The S1 is first shift with one stop, the S2 is the second shift with one stop, and stop 2 and 3, and then the whole data is an array with 2 shifts. Okay? The type of the thing is exactly as I told before. It's a row of area entity. It's nested. We don't want to have this, especially in the case if we, like here, we don't have any stops in the second shift. Then the type is something even more complex. So let's introduce fix point. We just wrap everything we had before in fix. Nothing else. Just a fix applied to every single row we had. And the final type is fix of row f. No recursion anymore. It's plain. It's recursive inside, but it's plain for the compiler. The recursion is in the type. Nice type. Yeah. So the library, there are 2 libraries actually for working with fixed point types and recursion schemes. Matryoshka and another one which is based on Scala Z, and another one is Turtles, which is based on cats. The Turtles is not production ready yet, as far as I know. So I will show you example with Scala Z. Okay, how do we read the data from the database using those types? This is what we get from the database. It's just like 5 entities I've shown you before on the diagram. They are related. This UUID represents the relation to the upper entities. So we want to get a fix of row f from entities. Or more generic, from some type A, we want to get a fix of f. Let's have a function which does this. But we can reuse the functionality we had before. Before we had functionality for constructing the entities from the data type. So now we just want to reuse it somehow and get a fix point structure. Easy. For that, we need somehow the notion of recursion, because we want to have a plain function and we want to get out a fix which is recursive. And this is how we do this. We represent this notion of recursion as a functor, and it's don't be scared. Like this is all boilerplate. We take a function from A to B, and we just apply it to the children using the map function we already have defined on sequence. Nothing which you could call complex. Okay, using this functor, we denote that we need a functor for type f, and we can get rid of this recursion blah blah, and that's it. So how to implement it? Just following the types. We wrap the result of applying f of a into fix. We still have no recursion here, so we use the functor to go down first. So we apply fix to result of the application of the functor to the result of f of n recursively. And that's it. That's called ANA in Recursion Schemes language. And as I said, those names, they are kind of strange and intimidating, and I have my own strategy to deal with them, like this. No, that's not a really anamorphism, that's anamorphism, and it makes a recursive structure out of non-recursive structure. So we have our function that we rely on, and this is a coalgebra. And we actually have 5 more seconds. I will show you how this coalgebra looks like, just so that you can see that we really don't have any recursion anymore in this definition. So for stops, the bottom layer, we don't do anything. We just return the row, right? For another layers, like in this example, in the sequence of orders, we take all of the stops which belong to this order and push them down. You can see that the type of this thing is entities. So this guy we're returning, it's kind of strange because it has the entity here, and it's supposed to have children of some type entity as well, but it doesn't. It has the children of type entities, and our recursion scheme takes care of taking these type entities and converting them to the proper entities type recursively. That's the whole point. You're not doing recursion here because the care is taken by the recursion scheme. And so it goes. You probably cannot read this, but basically this is the definition for all 5 of these different entities types, and they are very similar. The only difference is that just we return the same time as an input in every case as children. And another good point is that it allows us to implement this use case quite easily. We just throw out the cases we don't need. So here I just left 3 of them instead of 5 because I don't need to process to others. Even better, we can define each of the steps as a partial function and then build the coalgebra as a combination of them. So the composition is really great in this case. And this is how the Matryoshka library allows us to work with this. We take the whole input, we apply an anamorphism to that, use the coalgebra we defined. This implicit conversion is provided by Matryoshka in order so that we can call anamorphism on our input type. Okay, and that's it. That's our implementation. We get fix of rho f by combining partial function, each of them describing a single step of processing without any recursion. So if you like, we already 3 minutes over the time. If you like, I can show you another one, another direction, or we can make a break. Yeah? Okay. So let's imagine we want to return the JSON from this fixed point, from this structure as it is. The approach is the same. We have a collapse function which needs a functor representing our recursion, and we already have it. We don't need to do anything. We just need the function which goes in the opposite direction from f of a to a, and an input of fix of a. We are getting the functor from the outside, summoning the functor, yeah, and then we apply it to our to the value of the fix, unfix, and apply the collapse function recursively, and return the result. And by the definition, you can see that the collapse is actually working bottom up. This process called catamorphism, like another strange name, or catamorphism, which it converts the recursive structure into some value. We need the algebra for that. That's coalgebra is the opposite direction. And having this, it's as easy as this. Like as soon as we have those imports in scope, the same story. So we have here a row, and the children, strangely, if of type are of type JSON already. So we are not doing anything more complex than converting them as JSON using Kirke, and that's it. So the interesting part is this guy. It's not an entity as you would expect. It's just some sequence of JSON. because in the bottom-up fashion, the bottom rows are already converted to the JSON by the catamorphism. And yeah, this is how we apply it. And those guys, what we needed except our functor, which describes our structure. Yeah, I have a lot more, but we are out of time. Thank you. If you have questions, let's do it after the talk. One small off-camera topic, which I promised to do. Those people in the company I'm talking about, they of course hiring, so I promised to tell about that. Actually, I even promised to show this QR code for the case if you want to apply. And I have like a book to give away. If you like, just approach me. I have one copy. That's not for really beginners. Yeah, that's it. Thank you for your time.